Good morning, science class. Today we're going to be talking about the issues and a lot of these environmental impacts. We've spent some time studying and looking at some of the organic chemistry molecules, practicing with the functional groups, looking at these hydrocarbons. Now we're going to be looking at some of the issues that arise with the use of these different substances. The first issue we're going to look at is a simplified version of ozone depletion. So the first thing that pops up is there is natural ozone cycling. And so UV radiation collides with this O3. So remember, O3 is ozone. And this prevents harmful forms of radiation from actually reaching the Earth's surface. This is very important because it blocks out a lot of these harmful UV radiation that comes in from the sun, and it helps us to actually live outside and not getting very, very bad sunburns. And what we're learning with a lot of this high exposure to sun rays and UV radiation is, again, it's cancer causing agents. What happens is we have these CFCs, and when they're released, these CFCs are carried into the atmosphere, and these winds carry these CFCs all over the place. What happens with CFCs? They're exposed to these high levels of UV radiation, and so from that intro screen we saw we had the troposphere, but when we get into the stratosphere, where the ozone is, they collide with this UV and they actually break apart these CFCs, and this UV radiation produces excess chlorine atoms. These excess chlorine atoms react with that ozone and it actually breaks apart the ozone and it pulls apart the O3 and it makes an O2 and just a free oxygen molecule. This increases the surface UV radiation because now there's no ozone, it's been depleted, and now the ozone layer can't stop the UV radiation, and so that means the surface of the Earth has higher concentrations of UV radiation, and this is very, very dangerous because it causes DNA mutations in us, can lead to skin cancer, it can be very damaging to plant and different animals because they are prone to this radiation just like we are. They need the ozone just as much as we do. And so the main sources of these CFCs, and we'll talk more about it on the next slide, are things like refrigerators, aerosol cans, air conditioning units. So what is a CFC? I talked about them on the last slides and I said CFC, CFC. Well, what it is a chlorofluoral hydrocarbon, and that's what the CFC is. And you can see it in that picture above, where you have a carbon atom and it has chlorine and fluorine. And so this is why it was so important to learn about these functional groups on these hydrocarbons, because we're going to start talking about things like these CFCs and all these different types of derivatives. And we're going to see why benzene rings and all their derivatives they persist and why some are so volatile. Here, this CFC, you can see it reacting in the stratosphere, and so that lighter blue is the troposphere. That is about the first 15 kilometers of atmosphere that we live in and where we can fly all our planes in and everything else. But in this upper atmosphere, in the stratosphere where the ozone layer is, these CFCs actually accumulate because while they're a gas, they rise up. And you can see a free chlorine breaks off with this high energy UV radiation, and it actually attaches to that O3 molecule, pulling apart the oxygen to make a oxygen, and then it pulls apart to have a free oxygen. But it doesn't just stay with that oxygen and locking it up. Then that chlorine atom also just drops it, attaches to somewhere else, and it keeps breaking up. And so there's more than one, and all these different chlorine atoms, they keep just breaking up the ozone, then breaking apart again, and they keep reacting and pulling more and more oxygen. So it's a very much a positive feedback loop. With more chlorine, they'll pull apart more ozone, destroying this ozone layer, all coming back from these CFCs or these chlorofluorocarbons. So for some time now, we've seen that there's this depletion in our ozone layer. And for like something like the last 40 years, we've been recording and trying to measure the layers and the thickness of the ozone layer. The way they do it is they use something called a Dobson unit. And so you can see there's all kind of details of it. And so this data is collected from both the satellites and these big weather balloons, and they're made to travel all the way up into the stratosphere, and they'll collect all the data and they'll send it back so we can record and monitor how much gases are actually up there, what is actually happening, and we can record the thickness of it. Here's just another larger image about how these little breaks are happening, and we can see these harmful rays coming in through these holes in it and why it's so damaging. And you can see on the graphic where the CFCs pull apart the ozone and then they release a free chlorine, and then that chlorine frees up again because it releases to another chlorine, and it just keeps layering and layering. And here you can also see the layers of the atmosphere with the troposphere and then the stratosphere, and now how we have these harmful rays reaching the Earth's surface, all coming back from our own emissions of CFCs because we used them a lot as a refrigerator coolant, and that we used them in air conditionings. And once we started using refrigerators to keep our food cool, we needed something to actually have it as a coolant. And in the troposphere, in our level, it's very, very neutral. It doesn't react with anything. We thought it was great. However, when it gets to that upper stratosphere, when it had the UV radiation that is already being blocked out by the ozone, we saw that there was an underlying effect of what happens with this high energy and how it breaks apart. So something we didn't think of or know about back in the 1920s. So what does that extra chlorine actually release? Well, it releases these free radicals, and this can be applied to any chemical species that has an unpaired electron in their valence shell, and that's what the chlorine is doing, is it's ripping apart, but then it's creating these free radicals. When we're looking at these oxygen radicals, there's many different types. But those of the most concern for us is oxygen because they're reactive to oxygen species, which is dangerous when you're hearing it. It's like, well, we need oxygen ourselves. And so this electronic structure allows it to be very susceptible to radical formation. And we're going to keep learning about why these free radicals are so dangerous. Here you can see all these different oxygen species and how oxygen actually appears. Most times we see it as oxygen as O2, but we have peroxide where it's O2, but we have a 2- charge and it makes it very reactive. What we're actually seeing is the differences between the hydroxyl radical, what we see here, and the hydroxyl ion, what we see here, and how we actually have this free electron that is not actually paired up, where the hydroxyl ion right here has been paired up. And so this radical makes it very, very dangerous. This is dangerous to us because these free radicals, and so it's happening in the upper atmosphere, but it can also come down to us. What we see is these actually react with the phospholipid layer in our cell. And that's dangerous because it can react with the proteins and then the DNA, and it can damage these components of us at the cellular level, and it causes this tissue damage. What you see in my image is foods rich in antioxidants. And so this can be eliminated with these free radicals based on our food choices, because all these different vitamins or these different little particles or minerals inside of food are actually well known as antioxidants. And they're available in most of the fruits and vegetables we have. And you can see, looking around that circle, they always kind of promote, oh, rich in antioxidant, rich in antioxidants. Well, this helps eliminate these free radicals that are appearing in our body and helping our cells not get damaged. So there is some positive news. When this program was put together and talks about it in our textbook was put together, it was about 15 years ago or so. But now there's record-breaking news that in 2020, the ozone hole actually closes. And so December 29th, 2020, the ozone hole actually closed up. And so this is big, big news because it does cycle a little bit, but for the most part, what we're starting to see is real progress because we'll talk about the protocols that we put into place by countries, and we'll talk more and more about it. But we're really making strides to changing the environment. So this is one of the good positive notes that learning about this is here you can see where the ozone hole is. Typically it's over the poles like we see here. So we're looking at the top. So this is the South Pole. This is the North Pole over on here. And this is just where the CFCs accumulate and collect. But what we're starting to see, this was the before, and this is the after. And what we can actually see is the holes are starting to actually close up. Here I also wanted to mention about some other main harmful chemicals that seem to pop up, and there are more of these examples that we see over and over and over. The first two, dioxins and furans, you can see they're the byproducts of where chlorine is being used. And you can see right away it's these benzene rings, and then they have chlorine attached to them in little bits of different organizational structures, but really almost very quite similar. Dioxins and furans come from the paper industry and from bleaching paper, because when you think of it, paper is just cut up little bits of tree, right? When are trees ever that white? And so this is part of the industrial processing that can happen with these fumes. And if these fumes are just let free, well, you can see these benzene rings and they persist, but they also have these chlorine molecules which can become reactive. They can become very, very dangerous. Another one that's a big issue is something called DDT. If you want to read it out and try to pronounce it the whole time, go for it. But DDT is commonly used as an insect repellent, and in some places it is still used today. And it is very, very dangerous because not only can it be linked to cancer causing, but it also is very, very dangerous and it just persists. So remember, we had these POPs, right? These persistent organic pollutants, and it doesn't break down and it causes issues and it can bioaccumulate. Lastly, we have these PCBs, and this is where we have it in commercial use. And so the dioxins, furans, and these PCBs, or the polychlorinated biphenyls, are kind of the three major ones from industrial processes that we see. This PCB is kind of a range of different oils and a waxy substance, or it can be very thick. It's used as lubricants. It's used all over the place in many different processes and in industrial workplaces. These are all examples, and you can see the recurring theme when they're drawn out is that ring. And many are carcinogenic because they just persist and they don't break down. And that becomes the issue from this industrial processes if they leak or if they enter into the environment. Another big environmental impact that we're going to focus on is this photochemical smog, or sometimes people just refer to it as a smog. And they're coming from these VOCs. And remember, if we remember, VOCs and POPs are the big ones. So these VOCs are these volatile organic compounds, and they can be found in fuels and paints and solvents, and again from these industrial processes. We're going to see that they're two very similar and they're linked, and there is some overlap where some things can be both. They can either be one or the other, or a lot of them are kind of hitting in both of these VOC or POP categories. These VOCs, though, the dangerous part about them, and what we're kind of adding on to, is they can actually react and form ground level ozone. This is not good. Ozone is supposed to be kind of up in the stratosphere. Ozone can be very much an eye irritant. It can cause respiratory system distress. It can be very, very damaging to crops. And so this can lead to very bad effects to different types of plants. These NOx emissions, so if we remember, we had from chemistry where we had NOxes and SOxes, those NOx and SOxes. Well, these NOxes emissions can also result and help aid in this ground level ozone, which can be very, very damaging. Not such a good thing. If you can, pause it here or look on my online notes and you can kind of see how this smog and leads into this ill effects. So here are some of these dangerous parts to VOCs, or this effects of this off-gassing, as we're going to call it, when we release and things that lead to smog. And so if we remember the forest fires from a few years ago, how some people would have very bad eye, ear, and throat irritations, they would have headaches, or it was very hard to do any kind of physical activity. Well, imagine that's all the time, because it was very hard to do things when we had all that different ash and soot. Luckily, our air can clean up, but if you're always in that area where you have this smog and having these odors and things reacting, that's not so good. I like this graphic because it's just a generalized graphic, and so it didn't really relate to any area in particular, but in general, it's these industrial processes, or when we're creating and manufacturing things, this is where a lot of our VOCs are going to be coming from. And so the big focus is on road transport, but really it's quite a small little thing. It's a big component, but really, the big targets need to be in these industrial and commercial products, and if we can start reducing those, that might be something. Or if we're checking on measures, or we're trying to meet emission standards. And that's the big thing, is we know where the problems are coming from. Now we can work on fixing them. Since we've been practicing with some of our organic chemistry naming and practicing with it, I just wanted to give a few examples of what VOC molecules can actually look like. And you can see even these examples of paint, and having this gas released from paint can be dangerous. And so imagine if you worked as a painter and paints contain these substances, or if in your house and the paint just keeps leaching off. You don't want to be living in a house where these bleed off. So the more we start learning about these impacts, the better we can actually be at problem solving and reducing and eliminating these in use. So I talked about off-gassing from things like paints and solvents. Another big one is pesticides, and not all pesticides are created equal. We're going to talk about them and how they can either be highly targetable, or are they just killing what? And so we also have the terms insecticides, herbicides, fungicides, and depending on what their actual purpose is. So when they always just say pesticides, it's a very umbrella term where it just covers a bunch of different things. But here you can see insecticides and the different types of organic compounds they use, where it's a halogenated hydrocarbon, where a fungicide is they'll use these phenols to actually attack, or these various organic compounds to actually target herbicides. And so they're slightly different, so they could become a little bit more specific. All, though, can have the same overarching impacts of where overuse can actually accumulate in larger organisms. And we're going to keep building on that. So when we're talking about pesticides, we want to look at a couple different things, whether they have a high target specificity, so they act on a small range, or if they just want to hit one type of species or insect or plant. Sometimes you can just have something that just kills all plant life. Like if you want to get rid of all the weeds on a concrete surface, just kill everything, grass, dandelions, different weeds. Sometimes you just want a dandelion killer, but leave your lawn alone. So what do you want? Do you want a high target, very precise, or do you want just something that is very broad, where it just targets everything and it'll act very generally and it affects many species? Knowing this, regardless of it, pesticides should not affect the non-target organisms. And so this is something where we need to really think of, okay, if we have a pesticide, and let's say we want to kill all these insects, will it also harm later up higher on the food chain? This is where we come up with these two terms, this LD50 and LC50. This is terms for lethal dose that kills 50%, and then the lethal concentration that kills 50%. So dosage and concentration, the dosage could be given all at once. You could think of it maybe like a solid. The concentration would be if it's in the air or water. And would it kill 50% of the population within a specified time? And so what you would want is something that can kind of kill. However, you're looking at how does it affect the organisms. And so lower than this 43 milligrams per kilogram equals highly toxic, meaning anything lower than that, you require very little to actually kill 50% of the target. And so this can be dangerous because if you're spreading it and it gets more and more concentrated, well, animals can only handle a certain amount. And so if it has a very low rate and a very low dosage to kill, that can be very damaging if it actually gets into the environment. The issues with using pesticides and this lethality is because they spread. There can be drift because of wind or air currents. Depending on how you're spraying, they just stay in the air and they can accumulate on a windy day. Or the big thing is called a grasshopper effect. And just think, just like a grasshopper, how it hops and it leaps, you can see where they might spray in warmer climates, and then they collect and they condense, and then they move towards these poles. It always seems to kind of, they drift towards the pole. And you can see that on the image here, is they're spraying it here, but then it's carried, and then it's carried, and then it's carried, and it accumulates and it affects these poles. That's dangerous because we typically live right about up here, right on top of these accumulation zones. And so this example of these synthesizing esters of this 2,4-D, well, that's just a type of a pesticide and the effects of it. But carrying and having this grasshopper effect where it jumps and it jumps, accumulates, and it can cause these concentrations to get higher and higher, and all of a sudden we get towards that lethal dose and going higher and getting it more and more concentrated. Well, that's not good for ecosystems. Now we're kind of coming back. Remember, we're talking about POPs, these persistent ones. They don't break down. And so pesticides being persistent, they stick around for a while. These pesticides that contain halogenated hydrocarbons become very, very stable, and they contain these benzene rings, which again, they have this persistence. They stick around and they don't break down. If we ever see that picture, remember it's like pesticide application, please keep off. Well, usually that's put out because they just sprayed it. They don't want to get it on your hands, and you don't want to be ingesting it because, well, potentially they could have a very deadly pesticide sprayed out. It might not kill you right away, but you might feel some toxic effects. What they're waiting for is for it to actually soak into the groundwater and to actually go into the roots and get washed off with the next rain before you can actually play on it. And they're hoping that it becomes less and less. And what's happening is it's spreading around everywhere too, and it's building up accumulation. So that's why a lot of the cities are very hesitant to actually just spray these broad spectrum pesticides because, well, they persist and they accumulate and they accumulate. So there is more to talk about these POPs, but I just wanted to pause here. We're getting long enough. You can see here these dirty dozen of the POPs, the most common ones. Recurring theme is a lot of these are pesticides. And then at the very bottom are the big four that we kind of talked about, the DDT, PCBs, dioxins and furans, how they come around. Those are the ones we come up with. But you can see all these other ones. Oh, like right here, this hexachlorobenzene. Oh, we see benzene, we see chloral, we see halogens and benzene rings, and they're persistent, right? A lot of these pesticides, whether they're insecticide, herbicide, right? They stick around. And that's the dangerous part about these POPs is the persistence of them. So pause there for now. Make sure to take good notes on some of the key points as we're working through it. I know it's a ton of information and it's a little bit different, but kind of key notes of, oh, what is a PCB? Where does it come from? Dioxins, furans, how do they pop up? And then we'll see some questions about it. and where do we need to target our studies to. So for now, go through this environmentalism, and then hopefully Thursday we're back in class to talk a little bit more about it. Take care for now.